All right, thank you so much for the invitation. It's always wonderful to have an excuse to come back to Italy. So keep doing what you're doing, Daniele. So most of this work that I'm going to be talking about is joint with Senia Fedosova at Münster and Stephen E. Miller at Rutgers and Danilo Rodchenko at Lille and Don Zagier, everywhere. So, so I figured being one of the few people from the US here, I would start by fixing where is Kansas State, and as my badge appropriately references, it's in Manhattan, but not the Manhattan that you've heard of, another Manhattan, and I was trying to describe where this is, and it's in the very center of the US, but of course there's many ways we could take a center of the US, so we could take the geographic center by area, which is up here in South Dakota. This is, very important lesson in geometry. But, that's when we count Alaska and Hawaii. We could also take it by population, which would move over here somewhere in Illinois. But but Alaska and Hawaii, we're going to throw those two out. And if we throw those two out, then the center is right here where you'd expect it in Lebanon. And right next to Lebanon, about 130 miles southeast, is Manhattan. But of course, there's another Manhattan, so it's not the other Manhattan, it's this Manhattan. And of course, there's another Lebanon, which is not pictured in this image. There's a Lebanon or a Manhattan. Okay, good. Okay. So anyway, it's great to be here. So thanks again. Okay, so my talk is going to be centered around different methods for solving differential equations involving Eisenstein series, specifically of this form. And I'll just be mostly talking about SL2Z here today. And so here, the Laplace-Beltrami operator is y squared times kind of the usual Laplacian on R2. On the right side here, we have a product of two non-holomorphic Eisenstein series, which we've seen a few times now. So you can write as a nice kind of double lattice sum or a nice Poincare series, or you can expand using a Fourier expansion here. And here in the Fourier expansion, we have these leading constant terms are kind of the most problematic piece. These are not L2 functions on this space, but the rest of the non-zero modes here have nice rapid decay. And so this is kind of the setup of the differential equation that we're going to look at methods for solving. And as has been referred to earlier and discussed nicely by Kong-Kao, in the literature, these solutions are usually referred to as generalized Eisenstein series attached to particular parameters. So here, R is just a parameterization of the eigenvalue in this case. Okay, and again, as Kong-Kao really nicely summarized, and I could not do justice, one of the reasons we care about solutions to these functions is they show up in the coefficients of a low energy scattering amplitude for graviton in type 2b string theory. And then they also show up, as we saw in Kong-Kao's talk, in certain correlation functions in Super-Yang-Mills theory in this 1/n expansion. And these two things are linked by this ADF-CFT correspondence. So another place these things arise that hasn't been talked about in a lot of detail this week, but most people here are quite familiar with, is that they also appear at the depth 2 for modular graph functions, which have been studied very extensively. So specifically in the modular graph function case, these a and b values that would be integers, which would mostly be interested in. But in the first two of these contexts, most of the cases we're going to be talking about, these are half integer valued Eisenstein series. Okay, so what I want to do is I want to talk about 3 different methods for solving these differential equations, and I'm going to talk about kind of the pros and the cons of each of these methods, and then maybe kind of like where things stand a little bit, and maybe what we're hoping to do. Okay, so one really nice way that was first introduced by Green, Miller, and Van Hove in their 2015 paper is to use Poincare series. And so um, uh, one thing I'll note is in this particular case, we can only apply this when the right side, well, when we're talking at least about half integer things, we're going to apply this method when the Eisenstein series is squared on the right. And I'll talk about why we want to look why this method that I'm going to talk about here only applies to the squared case in a moment and not two separate EA and EB on the right side. So in this case, we have a really nice parameterization of this product of two Eisenstein series. There's literally no reason that I moved the two in and out. It just was, laziness. But we can rewrite this expansion in terms of this TA function, and this is kind of really going to be the trick here, is rewriting this TA function, we can, as a function of z, where z is, of course, x plus iy, we can kind of do a change of variables and think of this as a function of x over y that has this form. So in that case, if we do this change of variables setting u equal to x over y, and we look at this PDE on each summand instead of the whole expansion, the PDE then reduces to an ODE in U, which is x over y. So it's this really change of variables that makes this method possible. And again, I'll show where that comes in a little bit more explicitly with this TA function and why that works in a moment. But for now, the idea is you write this thing as a lattice sum, but we're going to look at the summands here. And we reduce the PDE to an ODE on the summands. We solve this ODE on the summands for little h, and then kind of put things back in the appropriate variables using big H, and sum back up over all this lattice. Okay, and so this is our new gives us a solution f to this differential equation. So what's really nice about this solution is it's fairly general, and it works in a variety of cases, at least writing this kind of like Poincare or lattice sum solution for many A, assuming A large enough that the series converges, of course. Essentially, it works in any A, and in many cases, we can find a Fourier expansion using this lattice sum. And the way you find the Fourier expansion is basically the same way that you would write a Fourier expansion for an Eisenstein series, basically breaking things up the appropriate way, and using Poisson summation gets you most of the way. So as long as you kind of keep track of things. What Steve and, let's see, it was in that 2015 paper of Green, Miller, and Van Hove, in moving to the Fourier series in a particular case, ran into a little bit of an issue computing one of the integrals in that in that Fourier expansion, but we were able to later kind of resolve that. And at least in many cases, so the half integer case, and I think even integer cases, we're able to write a full Fourier expansion. Odd integer and general cases, the integral computations are a little bit, a little hard. So haven't been done yet. Okay, but the other nice thing about this is, of course, that this thing is naturally gamma invariant just by the way it is written down. Yes. Yeah. One day. Yeah, but I'm not saying that right now. So we'll see. We'll get there. So that's the goal. So I guess right now this method won't get us everything for any generalized Eisenstein series because it only works on diagonals, and the reason why this only works on diagonals is because of the form of this expansion. And here you can see from basically what you, doing this change of variables in the TA thing that we had before, if we look at the denominator of this expanded product, we have this nice property where this denominator, we can factor out an a, and then if we expand this denominator really nicely, we get these two terms, which match up really nicely with this ratio of the real and imaginary part that we saw in this TA function we had before. So I guess sorry, Shai, I'm like pausing on answering your question. I'm hoping to get a general thing. We'll see what happens. And for now, I'd say this method won't get us there for exactly this reason, that these, we don't have an analogous kind of identity that seems to be working out to give us this TA function that we were able to get our ODE on. Oh, I haven't, well, that's a good question. So when you look at the diagonal case, we've checked that the Fourier expansion, at least in the 3/2 eigenvalue 12 case, matches exactly with the one that is in Steve's paper, whatever, and in all these other cases. So what's that? But we haven't written out any other full Fourier expansions to see. So that's a good point that leads to some other things too. So actually computing the Fourier expansion from these things is, so even in that, that's one of the simpler cases in the D6R4 case is one of the simplest things. And I don't know how many pages we wrote up computing that one integral of that Fourier expansion, but it involved 7 iterations of integration by parts and moving contours and splitting up things, and it was a mess. So we haven't done it for every case, but we're thinking we might do some more. Yeah. So what happens actually is these little HAs, we have those, and we haven't, but as we'll see later on, the cusp forms come from the homogeneous part from the Fourier solution. So they're, so I guess they should be, yeah. We haven't looked at where it comes from in this part of the solution exactly. Yeah. So that's a good point. I mean, it matches up with it's a little weird, getting back and forth, but yeah, we do. You can, in principle, that's a good point, Daniele, is you can find these little HAs in general. This is something Mathematica does totally fine, and Don's not here to yell at me about that. But so these little H's in the half integer case just turn out to be rational functions times some arctangent function always. And in the even integer cases, they're actually just rational functions. In the odd integer case, that's the only part where going to a Fourier expansion is very difficult because they involve this weird arctan squared, so we haven't gotten around that. But in general, I don't know I haven't seen what a closed form is in general. Yeah, that's a good point. Yeah, so again, it really doesn't depend much on lambda in this case. So again, both can be general enough that things converge, I think. Yeah. So yeah, I haven't tested too much in practice, what is the solvability of all the ODEs within variations of lambda. That's a really good question. We only ran a few small examples in this case, so that's a good question. But we'll have more kind of input on that all those things, looking at other solutions as well. Okay, so good. Okay, so so as I said, right now, especially moving to a Fourier expansion, but even just in the kind of pre-Fourier expansion version of the solution, things are kind of limited. And so there's another method that we're just kind of calling guessing at the moment, that Ksenia Fedosova and I explored a little bit more in depth. And the idea for this method is basically, instead of taking the right-hand side and writing it as a product of the sums over the lattices, we write it as a product of the Fourier expansions that we already have here. And so in the Fourier expansions, basically we write this product of Eisenstein series as as a Fourier expansion, and then the coefficients are just functions of y. They really depend on two parameters, n1, n2, basically n1, say, coming from the first Eisenstein series, and n2, say, coming from the second Eisenstein series. So each one of these little coefficients really looks like, I don't know, maybe some polynomial or some polynomial times a Bessel function, or y times a product of two Bessel functions, say. So what we end up doing is a similar style thing that we did previously, which is we want to solve like a system of ODEs. So now what we notice is if I assume that my solution has a Fourier expansion, I write my, I make my, let's see, I look at the ODEs on each one of the summands of this Fourier expansion, and what we're left with is like a nice system of ODEs that looks something like this. Okay, and so this thing, I'll later just be calling L and R just because it gets cumbersome to write, but I'll put it up here later. But it's basically, this is just the Laplacian, but you can kind of ignore the x pieces because we're assuming this is translation invariant under that exponential, because our Fourier expansions only involve the coefficients are only functions of y here, right? Okay, so here we want to solve this differential equation, which is, again, just an ODE. But this time, Mathematica doesn't like it. And so this time, Don is right. No, I'm just kidding. Don is always right. Okay, so this time, this ODE is not nicely solvable in most of the cases. So of course, if this is a polynomial, it's not too bad. But if these things are products of k-Bessel functions, there's no nice closed form solution for something like this. And so what we use is, this is where our guess and check comes in, is we just use the fact that we know what we're saying, okay, what do I need? I need k-Bessel functions on the right side, so I should be probably taking derivatives of other k-Bessel functions on the left side. And I make myself a nice system of linear equations. So I take my operator, which is like y squared times second derivatives and some linear function, times each one of these little basis elements, and I know it's going to be some polynomial times other k-Bessel functions, just based on this derivative thing. And what I'm also kind of hiding in the weeds here, did I erase it? Oh, I might have erased it. Is there's also a kind of lowering type of, you can think of like almost like a lowering operator that takes, since all of these, if we're talking about the half integer case of A and B, these k-Bessel functions, where A and B are, this is not the same A, but if this A and this B are half integers, each of these can be expressed in terms of polynomials times k0 Bessels and k1 Bessel functions. So we're just kind of lowering the degree based off a really nice recurrence relation that I can put up here if that's confusing. But yeah, I end up with this nice system of equations. Okay. Okay, so I end up trying to solve this system of linear equations by kind of this guess and test thing, and this is something that, well, Mathematica also can't handle, but Python can, and presumably Paris can, and such. And so we do this, and we get a nice closed form in a lot of explicit cases. And so I write this as a conjecture, because we have it written down explicitly in a bunch of cases, in a bunch of solutions, but we don't have it written down in full generality. And so the idea is, okay, you're looking for a solution of this PDE. We'll assume it has some sort of Fourier expansion. We're also going to assume a couple of growth conditions on F. And the reason for this is these assumptions come from Michael and Steve and Pierre's 2015 paper, where basically this condition is coming from the fact that we want our solution to be not just translation invariant, but inversion invariant, so fully automorphic. And so So once we impose this condition, this gives us a unique solution to each of these differential equations, so it uniquely picks out a homogeneous solution as well. And so this looks like a mess, and it sort of is, but the idea is that we get kind of a basis of k0, k1 Bessel functions, and then polynomials in y and 1 over y, so not too bad. F is also a polynomial in y and 1 over y, and then we have this k Bessel function that's not 0, 1, it's dependent on the eigenvalue, and this whole thing relates to the homogeneous solution of this equation where we force these boundary conditions. And so that's what's giving this term, okay, in purple. As was noticed by Chester, Green, Pufu, Wang, and Wen, it seems like this coefficient should have been 0. And this was mentioned in Konkow's talk as well. So we'll talk about, and so this is where our cusp forms are going to come in, is with this homogeneous part of the solution. And so just to summarize, I guess, we have this written down explicitly in some cases. There's a few conditions, right? This is only for the half integer case, and it's for particular values of a and b that I'll emphasize a little bit more later. We'd like to be able to prove this in general. What we really like is a closed form for these coefficient functions. But as you see, by looking at the examples, they're quite involved, and so this isn't that bad, but then when you really put the m's in, oh my god, it's a mess. Okay, so we'd like something a little bit more something we can deal with involving like some generating functions or something like that. And so we'll talk about those ideas. So the idea, so to touch back on this homogeneous solution, I'll just say, as an aside, so this is again where these Fourier coefficients of holomorphic modular forms of full level are coming from, is from all of these alpha n's. And so specifically in the D6 R to the 4 case for the 2B scattering amplitude, what happens is based on the eigenvalue and the A and B that were chosen, the Fourier coefficient turns out to be for the cusp form of weight 8, and so there is no cusp form of weight 8, and that's just 0, and this is nicely just 0. In other cases, like when we choose A and B to be 3/2 and we pick a larger eigenvalue, this was the first time we saw, well, maybe this wasn't the first time, but we see a nice, this is the coefficient of the Ramanujan delta function, the Fourier coefficients over n cubed, and then weighted by a nice like L value. And again, we actually get these, so just to emphasize, not for just this weight 12 modular form, but for any weight that you like, we can find a cusp form of that weight. So here's the pairing A 3/2, B 5/2, and this large eigenvalue of 132. We can find our weight 24 cusp form, which is just a linear combination of the two. This was the first time that you really have two cusp forms of weight 24, and it's a nice linear combination of those things that we spell out explicitly in our paper and such. But these are a couple of nice examples. And as Konkow really nicely mentioned, when you're looking at something like the integrated correlators, since we're taking a nice linear combination of all of these generalized Eisenstein series, all of these cusp forms end up canceling exactly, which is really surprising, and I mean surprising to me. Yeah, it's explicitly defined. I just weighted stuff annoyingly. It's not 0. Yeah. No, it's not 0. I just put a constant there just because, it's explicitly defined, but I didn't want to figure out my reweighting of things and say something totally false. But if in the paper it's all explicitly written out based off of, I think the weighting we chose for alpha n was like slightly different than is like before, so I don't know. I hate writing false things. So that's also why I have a quotes. But it's not 0. Good. Good question. Okay. So then Good. So there's a few things about this solution, and we'd like to be able to generalize this, and we'd like to be able to prove this kind of in full generality and write a closed form. But there's, and in fact, let's see, when I wrote this version of a conjecture up a couple years ago in the Newton Institute, Don yelled at me and said that this is obvious, and I'm glad he now agrees it's not obvious, that this statement might be true, and there's more to proving it than we thought. And so I just want to talk a little bit about how there's more to proving this thing in full generality than we had originally expected. And so in ongoing work with Don and Ksenia Fedosova, we have been kind of working to write this closed form in generality and showing that this thing works. So what he had thought was, well, and I think if we didn't have this y here, ln r, if there were no y in this part of this basis v, say, where I and j are just taking over all integers, then this ln r would actually be a vector space isomorphism. And this wouldn't be a really big deal, I don't think. But this y kind of throws things off quite a bit. And so in our construction that Ksenia and I did to do a bunch of these computations, what we did was we basically assumed f is going to be in something like this basis, okay? But in fact, depending on which cases of A and B and which eigenvalue you're looking at, this basis really breaks down into two different vector spaces that are kind of disjoint. So in most of the cases we're thinking about right now, we've just been looking at this even case, and I'll say what that means in a moment, but it basically just means whenever you're applying L and R, you're never gonna get well, it's basically all the cases where you're gonna get, say, 0, 0, 2, or something like that. So these are even pairs, so we'll see in a moment here. So for instance, if I assume A plus B is even, then kind of my basis that I'm thinking of acting on has this form of y to say, if y is to an odd power here, then these things have to be mixed. And if y is to an even power, or assuming 0 and negative even numbers, then these coefficients on my k-Bessel functions have to match. So you'll kind of notice there's no y's times k1 k1, or k0 to k0, right? So there's this kind of weird thing that happens with these basis elements on which L and R acts. That splits that general vector space, big V. And so specifically, you can write LNR on this basis, and you can write it as a nice functional on this basis of FMs. And what it does is it takes something in FM, and that solution space is generated by FM minus 5 through FM. So. So there's this kind of weird, dropping of weight that kind of throws things off a little bit. And more specifically, what we see is that not only is LNR not isomorphism just on V, it's not isomorphism on V even either. All the time, at least, I should say. And so in order to get LNR to be an isomorphism, we kind of need to take, we have it nicely that we're able to show so far in preliminary work, is that we have an isomorphism between these two bases and some other characterizations of them. And so what you kind of see is you really end up kind of dropping down, and there's like this shift that happens, and it's, it's a little bit, it's not as clean of a translation between these vector spaces as you would hope. But so what we are able to show is kind of what appeared in the previous slide, is at least we're kind of have it in some cases, is that if A and B are small with respect to the eigenvalue, then then something like this will be in the image of that basis V even. And so where we're going to have a solution in terms of basically, if you look at the original conjecture, we are able to show that, at least in the case here, where A and B are small, we should be able to have a solution written in this form. And right now we just have a proof, something akin to a proof for the parity of A and B matching, or A plus B even, I think it is. And sorry, the parity not matching, I think it was actually. And we're working on things in other cases as well. But that involves the other version of the vector space, so we're not there yet. And then what happens is once we move out of this region, there's an obstruction, and that obstruction is actually given in terms of like Rankin-Cohen brackets. And so this is like definitely still work in progress, and we're kind of working towards it. I mean, so far it seems hopeful that we should be able to show that this is true, that at least in these particular cases, this is the form of the solution. And then we're really hoping to work towards getting an explicit closed form for those coefficients. I should have said as well that we're hoping to get the closed form for the coefficients partially based off of this prior work of how we were able to write kind of a basis of elements in terms of these sigma divisor functions. So there's a few places we're trying to look and put things together, but things are more complicated than we had hoped, than everyone hoped. Okay, so in kind of summary for this method so far is that in practice this method works for most cases of A and B half integer, as long as they're within that range of A plus B, or sorry, A minus B being less than R. But unfortunately, there's no closed form for the solution. This is something we're working towards. And right now, the way the solution is written, it's really difficult to use manually. These things are just complicated. And worse, we don't know for sure that they're all automorphic. And we have no evidence right now to show that they're not. But we don't have a proof that they are either. And so something else we're definitely working on. Okay, and so I'm hoping that, yeah, I guess if we can write a cleaner, I should say, oops, got way ahead of myself. I'm hoping if we can write a cleaner solution and a closed form for those Fourier coefficients, then automorphy will be a little bit more reasonable. Yeah. Correct. Sorry, in the, yeah, let me find, oh, sorry. Mm-hmm. So, so, I mean, these ones are just like changing the 0 and 1. These ones are over all n1 and 2 that sum to n. And so this is all n. Yeah. Mm-hmm. Well, I mean, no, this is like finite in terms of n, but you were summing over an infinite thing. Does that make sense? Oh, yeah. In particular cases, I do. Yeah, sorry. Yes. Well, no. So what I should say, maybe I can clarify. So in specific cases of A and B and lambda, so of the values for the Eisenstein series and the eigenvalue, computationally, I get a nice closed form, like in terms of n and n1 and n2. But it's only computational right now. And so that's in specific values. But in a general value of A and B, we don't, because we just use linear algebra with using a computing system to get those. And so these big M's are finite polynomials, but we only have them in a few cases. You give me your favorite, my computer runs your favorite, and I can find it, right? But I don't have like a closed form in which varies over A and B, if that makes sense. Does that answer your question? Okay. Sorry, I try to spare people from writing the monstrosity that is these solutions, but let me know if I could clarify further. Okay, so yeah, this is just experimentally verified that in most cases. Okay, any other questions? Okay, so with a few minutes left, I'll talk about the last version of the solution, which has its own advantages and disadvantages. So the last version of the solution is something that Nathan Benjamin talked a lot about yesterday, so thank you for introducing this and making my job a little bit easier. So the idea is that is something that works really nicely in general, which is to solve some sort of differential equation, we can write whatever the right-hand side is, in this case, of course, the product of Eisenstein series, as in terms of its spectral expansion. And I would argue that this is a little bit more than a Fourier expansion, but yes, it's given in terms of an orthonormal basis of Cuss forms that we can show are discrete, and then the basis of Eisenstein series, which make up part of our continuous spectrum, and then some constants that come from a contour shift of this spectral integral and our residues of Eisenstein series. So this is one way we can decompose, but this only works for, well, I shouldn't say only, this works for S being an L2 function. It does actually work for distributions as well, but only particular types of distributions that products of Eisenstein series don't fall into. And so the idea is write out this full spectral expansion and then divide by the spectral parameters. So whatever your eigenvalues for your Cuss form and your actual lambda are here. So again, as I said, my problem is that my product of Eisenstein series is not an L2. It's not even in the inappropriate Sobolev space in order to write a spectral expansion in this form because of this constant term growing too quickly. And so what we do is we do just a little hack, which Nathan alluded to yesterday, which is basically subtracting off some amount of these constant terms. But we have to subtract off these constant terms in a way that's automorphic, so that it's still SL2Z invariant and I don't fall out of this part of the space. So I subtract off a linear combination of Eisenstein series. And so specifically what this looks like is for EAEB. Being this product, I have, of course, my constant term looks something like this now, and my higher order terms are still going to be rapidly decreasing even when I multiply them by y times this k-Bessel function, and y is fine. So I'm going to have, say, these 4 terms, and for A and B large, we can see that maybe this term is problematic, and maybe if A, say, is larger than B, maybe this term is problematic. But if A is much larger than B, then maybe the second term is fine and the 4th term is fine. So say for A and B large, I would subtract off something like this Eisenstein series where this term will cancel with this term. And yes, I'm adding something back in, but I'm adding something in that's really small, right? And I might also have to say subtract off an Eisenstein series at 1 plus A minus B or something like that. So this is what this linear combination turns out to be. It just depends on the size of A and B. And so when I do that, I'm able to write my form for my solution then, basically I write a spectral expansion for this stuff that is the product of Eisenstein series with Eisenstein series subtracted off, then I add them back in. And so here's the Eisenstein series that I had originally subtracted off and add back in. And here's the spectral expansion of EAEB minus a finite linear combination. So as coefficients for the Cuss forms, the basis of Cuss forms, I get really nice completed Rankin-Selberg L functions. I get occasionally some constants for particular values of A and B that are written down explicitly. And then the tricky part is really computing the Rankin-Selberg convolution of 2 Eisenstein series, but this is nicely done by Don Zagier in his paper on Rankin-Selberg for functions of non-rapid decay or something like some permutation of those words. So following basically that method using Arthur truncation and Moss-Selberg relations, we're able to compute this spectral integral here. So And we're able to do this, in this case, what's really nice is we're able to do this for any A and B complex kind of in this purple region. We can also meromorphically continue this to kind of the other side using the functional equations of these L functions in the Eisenstein series. So, you know, things over here are fine. What's less fine is, say, these dotted lines, which is basically the points where you maybe subtract something off your Eisenstein series, and then you end up adding something large back in. So in those cases, we're only guaranteed to have a solution when, say, these coefficients are 0, which correspond to 2a minus 1 and 2b minus 1 being zeros of zeta. So, so we can say something a little bit more specific, but what's nice about this formulation is it does tell us that there is a unique solution in all of these cases in this that is modular invariant. So that is, or SL2Z invariant, and that lives in this space. So even though in many of the cases, in the two different attempts we tried earlier, we, you know, can't always find a solution, this tells me, you know, actually, I'll say almost always, but I don't need it in the mathematical sense. I mean, very vaguely, a solution really does exist in some way.
In a previous talk, I think we saw
Geometric functions. Oh, that's fine. Yeah, yeah. So maybe that's like akin to this part or something, and I can't remember what you were computing it of. When you push it, yeah, yeah. Mm-hmm. Mm-hmm. Yeah. Good. Okay. Very good. Okay, so let's see. So you know, kind of as we probably can guess, working with these spectral integrals is not particularly easy, and kind of, I guess, is alluded to with these moving the contours back and forth, what was I going to say? So we can't write, you know, a full Fourier expansion for something using this method. You know, furthermore, we don't have an explicit basis of Cuss forms. We just, you know that they exist, which is a great, hard enough thing to prove. But yeah, we can't write all of them down and say work with them explicitly in some parameterized sense. And so, Doragoni and his student Trailis have shown that you can actually find the constant terms for the Fourier expansion using this method, but I think it's hard. I think there's, so far as I understand. Can't you find the constant terms of Fourier expansion with this spectral expansion? You've done that. The zero mode. Yeah. Wrong one? Was that? Oh, okay. Well, I think. Okay. I'll just cite you that you can do it. Yes, the constant Fourier mode. Yeah, yeah. Sorry. Let's see. And of course, like I said, we can do this for a majority of A and B. And then a similar style argument, I mean, it doesn't matter really how many Eisenstein series, assuming we have like a finite product on the right side, this I mean, in principle works, just becomes a matter of bookkeeping. Mm-hmm. But, sorry. Yeah, yeah. You mean, is it this part that you're worried about? I mean, I don't think anything's written down, but I think you. Yeah, you already have 3 here when you're doing this. No, but you, yeah, because this is a, no, because when you find this, you're multiplying this against another ES. So you're integrating, you're doing them with 3 Eisenstein series. You can do as many as I mean, you just have to keep track of stuff. It doesn't matter, you just unwind one. What? Yeah, you just have to pay him the sum of which one? You can't? Okay, I'll have to see. Sum on divisor sigmas. On like the yeah. Oh. Okay, I have to remember this part of it. Okay, I'll believe you. Okay, I believe you. I'll have to look closer. Okay, well, scratch that. Okay, so scratch my last comment, and I'll think more intensely about that. It does work. Yeah. 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 Okay. Okay. Cool. Well, then don't erase it. I'll see what you mean explicitly in a moment. Very good. So the other thing is, I mean, I guess I wrote this. Is this always possible? And what I mean is it possible? I mean, in theory, it should be possible, right, for this product. Is it possible for higher rank groups? And so I thought, well, it should be possible, if anything, on SL3 because we know a lot about SL3. And so, so specifically, when we look at this example for SL3, there's now, of course, 3 different types of degenerate Eisenstein series depending on the different parabolics that you have. I think the ones that show up in the D6 R to the 4 are these ones associated with the 2, 1 Eisenstein series over here, which is good because they're a little bit simpler than, say, the minimal parabolic Eisenstein series. So in something like this case, we can write out, say, again, a Poincare series for this Eisenstein series. We can also write out a nice closed Fourier expansion. This is, I believe, originally due to Terrace and Imani, if I remember correctly. And it has a similar kind of flavor to things that SL2 did. We have a similar kind of decomposition of this upper half plane in terms of X and Y, but of course X and Y just look a little bit different here. We have this X matrix and Y matrix. And so here I notice I have 3 terms in this 0 mode part of the expansion. And the only other weird thing is, well, there's a few weird things. I have 2 values of Y, Y1 and Y2. For this big Y matrix, say. And so these higher modes, these non-zero modes, are no longer rapidly decreasing because here, say, I have just a K-Bessel function in Y2, but there's nothing in Y1 to make this rapidly decreasing. And a similar phenomena happens down here. Okay? And so, I mean, a first question would be, can we do a similar game where I subtract off at least these constant terms? When I have a product of these 2 Eisenstein series taken together, so now I take, say, 2 Eisenstein series, each with 3 of these 0 modes, sorry, well, I should say 0 modes, or whatever, which I'm now going to get 9 terms, right, when I take the product, which is fine, a little scary, but again, it's not the minimal, so that's bad enough. So I get 9 terms, not too bad, and I can look at this thing and get a flavor for what's happening. So like, say I take A and B large. Again, I don't have to worry about this guy, and I maybe don't have to worry about at least one of these or something, right? There's a few terms that I can kind of ignore depending on the size of A and B. But you can see that it already gets a little bit more complicated. But the idea is that what I want to do is I want to match the powers of y1 and 2 with the original constant terms of the 2-1 Eisenstein series so that they have this similar flavor where they're either in this thing of a 2, like an a and a 2 times a, or a something and a 2 times that something, or a 1 minus a and an a, right? So I want something like this flavor going on so that I can find an appropriate amount of, say, 2-1 Eisenstein series, or this would also give 1-2 Eisenstein series, that would match to cancel these terms, right? So we can kind of quickly see some of these, I feel like, very nicely. Where is she? Like this one. This is a plus b and 2 times a plus b. So there should be an Eisenstein series that nicely matches up with this thing. So say the E2-1 Eisenstein series at a plus b nicely matches up here. The problem is kind of twofold. I can actually verify that it's not possible to set up. How am I going to say this? I can't do it for all of them at the same time. And yeah. Minimal representation. Yeah, I got. No, I could do the minimal parabolic and the maximal representation. So, okay, so I don't know for sure. I haven't proved to myself that I can't use the minimal parabolic Eisenstein series. The minimal parabolic Eisenstein series has 6 terms, and they depend on 2 parameters now instead of, which is nice, but I still haven't been able to find a combination to do it. So, I mean, I haven't proven to myself that it's impossible, but I don't know how to do it. So good. All I know right now is that it's not possible to do with the 2-1 Eisenstein series, and I feel fishy about trying even the minimal because there's this further issue with doing this game, which is that, well, with the GL2 Eisenstein series, when I say subtract something, say this term cancels, well, this term's going to be small, right? Because this one's the one I'm trying to cancel, but I'm still adding something that's not small in. And with the minimal parabolic, it's just going to be so much worse. Yeah, minimal parabolic, maximal representation. Yeah, it's possible, but I still have to get rid of Bessel functions. And so there's another idea here, and so which I'll kind of talk about in a moment, which is, so because there should also be something like this y times a Bessel function thing going on. So it really does feel like I'm going to need, it seems like the right kind of thing, and this is kind of alluded to by something I'm going to mention in a moment, which is, the right kind of thing that you would want is something like y1 times a GL2 Eisenstein series in y2. It feels right. It seems like things cancel and the things work out very nicely. The problem thing is that that's not automorphic in SL3. And so that's actually exactly so that's exactly what the issue is with kind of one of the other ideas, which is like maybe truncate and maybe just even kind of focusing on this Rankin-Selberg functions for not rapid decay, and kind of focusing on that method of maybe a workaround with just a truncation first. And actually, mathematician Lehman has done this extended Zagier's rapid decay paper to SL3, in fact, in this 2-1 Eisenstein series case. But in Lehman's version, he actually isn't able to prove the full like Rankin-Selberg thing, and so I think he is also not able to find something where you can subtract something off and remain automorphic. And so what he does is he finds something that's not fully SL3 invariant, but invariant under like the parabolic or something like that. So he has to like unwind first before he can do the subtraction. And so far that's the only way I've been able to see to do it and not make something that's, you know, so right now I'm like, well, maybe we can get a solution that's not full SL3, but maybe just. So in the interest of time, I guess I alluded to a lot of things that I want to try to do, and a limited number of ideas. And I spent the last 3 weeks thinking, maybe if I push one of them, we'll get somewhere to talk about something new and exciting, but I just gave you a concatenation of a bunch of stuff that I don't know how to do. So thank you very much for your time, and I appreciate it. Mm-hmm. 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 No, I think they're new. Yeah. No, they're new. I mean, I mean, new. I think yes. So many of the full expansions we like hadn't been found yet, and so they were new. Uh huh.
So can you learn from those as to
Yeah.
what would be the next least difficult?
Like case, or what do you mean?
Well, you have a general
Hmm.
you have concrete new suggestions.
Hmm.
You tell us about them, right?
Yes.
And they go to
Yeah. Uh huh.
98
Uh huh.
and 32, for example.
Uh huh.
You can't solve the general problem. So my strategy in life is always to look at the next least difficult,
Yeah.
not solve the whole thing. Find
Yeah.
out what was it about those special ones that
Well, I mean, there wasn't anything. It was the runtime on our computer, because since they were using like a computer algebra system. I mean, we can write them down explicitly. It wasn't. We can write any of them down that we want to. So we just can't, and so yeah, and so let me think. So I mean, we have a few next steps. What I didn't really say much about, but one of them being, so in the homogeneous solution, like we did when in analyze. Okay, taking say your train of thought and saying, okay, analyze the easiest part, right? So we take one of those solutions and we looked at just that homogeneous piece, and we were able to write kind of a nice generating basis for like the alphas for just the homogeneous piece. And so this is where I'm hoping we can get a generating set for this. And I didn't write it down, but if we can, let's see. Yeah, in these alpha n1 and 2, we can write in terms of their Jacobi functions of the second kind. So in just analyzing these, and I think the other coefficients have to have some other, it was just picking the right normalization and getting the right bases was really, it just took a while with even the zero mode. And so, I mean, probably working on other modes, knowing what we know about this thing, we might be able to tweak some stuff is another nice step, I guess. So as opposed to thinking of like, here's one solution, what's the next nicest solution? Maybe, okay, we were able to parameterize this homogeneous solution now in any piece. So for any A, any B, any eigenvalue, I can tell you what alpha n1 and 2 are based off of Jacobi. It's determined by a Jacobi function. But sorry, yeah, that's what I'm not saying this clearly, I apologize. Yeah, it just takes a lot of finagling to figure out what the basis dependence is and stuff.
So your first step is the Poincare series. I didn't quite understand why it's restricted only to perfect squares, because you would do like a double Poincare series.
Mm-hmm. Yeah, and you guys do a one Poincare series, right? But I think we can't. Yeah, and I haven't followed my all the way down to see what happens. I haven't. So yeah, I don't know what happens if you try to just do the one Poincare series but yes. And so I don't know but I don't know if, because what's on your right hand side a 1K Bessel function and an ODE with. Yeah. So then I think I think we still end up in part of the second case then, where we're solving the ODE, and I'd have to think about how that. I guess we'd have to combine methods, and that's this one thing I've wanted to think about, but too many things. Right. Yeah. Mm-hmm.